And now we'll continue working through 11.1. We'll get a little more practice and have a few more little pieces to add with sequences. By far, the biggest thing is just the overall introduction, the notation, and the understanding of how the limits lead to convergence, divergence. But as we keep seeing, there's a lot of little extras that are going to come up. We already saw a little bit with factorials, and now let's see another little situation. So well, again, that does the sequence converge or diverge? If it converges to what? Still sticking with that. I'm going to start over now. We've already used a lot of letters, so I'm going to go back to A, and let's look at the sequence. A sub n is n plus 1 over n all to the n power. So if we take that limit as n goes to infinity, well, inside of here, the dominant term, n over n, would give you 1, and then that's being raised to the n power. So it looks like this is going to 1 to the infinity power. And that's quite troubling. That is not an easy one to deal with. Remember, that is not 1. That is one of our indeterminate forms, and it was one of the bigger pain ones. This is where, well, we'd have to switch this to x because we're going to eventually use L'Hopital's rule. But we're going to start off by taking the log of the sequence so the exponent can kick out in front. There's really a lot to it. Now, this does not work for all 1 to the infinities, but the reason I wanted to bring this one up is because if you play with this just a little bit, n over n is 1, and then 1 over n is 1 over n. And do you remember in this form what happens when you take this limit as n goes to infinity? I hope that looks a little more familiar because we went through and done all that work already, so you can go back and do it again. But that equals E. That is the definition of E. So I just wanted that as another quick reminder. It's going to come up. I don't remember exactly when, but that's another one that kind of keeps sneaking its head in chapter 11. And if you have to do it by hand every time, it's a very long pain in the butt problem. But if you remember it in either of these forms, and you should know both of these, it's not that this equals E, it's as you take the limit it equals E. So that would tell me that this sequence A sub n converges to E. Okay, so that was just another converging problem, just a quick little reminder. The next big thing that we need to discuss, not as big as all the other topics, but something that'll come up a little bit, is the idea of an increasing and decreasing sequence. It's a little similar to increasing and decreasing functions, is as you go from left to right, if the graph goes up, you're increasing. If you go down, you decrease. But the idea, when we had regular functions, we'd often have periods of both. We're going up here, but then I'm going down for a little bit, then I go up more. So you'd have not alternating necessarily, but you might have multiple intervals of increasing, decreasing. Here, we only say a sequence is increasing or decreasing if it's always going up or going down. So A1, if it's increasing, A1 will have to be smaller than A2, will have to be smaller than A3, will have to be smaller than A4, and so on. I'm including the equals here. Some textbooks, especially if you go a little further along in something called real analysis, there's a difference between monotone increasing that allows for the possibility of your terms being equal or getting bigger. And I know this is a less than, but just think about this. 4 is less than 5. This one is bigger. 5 is less than 7. This one is bigger. So that's the idea of increasing. We're not going to worry too much about that. Again, some later classes might get a little more hung up on the difference between strictly increasing, where it's a straight less than, or monotone increasing that allows for the equals as a possibility. We're going to leave the equals to make our life easier. And same thing for decreasing. Now all the terms are getting smaller, So A1 would be bigger than A2, which would be bigger than A3, and bigger than A4, and that continues forever. That's what we mean by increasing or decreasing. The last little thing, you may get eventually increasing. Maybe just the first term doesn't, or eventually decreasing, either one. Maybe the first term, this is bigger than this, but then after, this is less than this, and this is less than this. So it would be increasing after n greater than 2, or something like that. That's okay too. We're not really worried about that, but just to realize that could come up, but overall, that's what we're looking for. Now, the book does mention you could use calculus. You could convert your a sub n into the appropriate f of x. You could do the Calc One approach, take the first derivative, set it equal to 0, see where it doesn't exist, find all your critical values, make your first derivative test interval. Everywhere the first derivative is positive, you're increasing. Everywhere the derivative is negative, you're decreasing. Only focus on x bigger than 1, and then you could see, hey, the function is increasing from 0 to infinity. That means the sequence is increasing. The function decreases from 1 to infinity. The sequence is decreasing. But plenty of sequences are neither. They go up, they go down, they do both, so you don't have to be one or the other, but you could use that Calc 1 technique. Some people like that. Most people start to embrace the sequence definition. So this is the general idea. So in general, a sub n will be smaller than or equal to a sub n plus 1. If that happens generically, well, if n is 5, a sub 5 is smaller than a sub 6. When n is 10, a sub 10 will be smaller than a sub 11. So if we could show this is generically true, that would show that a sub n is an increasing sequence. Similar for decreasing, except now it would be a sub n is greater than or equal to a sub n plus 1. So that's what I want to show you here. I don't want to get too hung up on this because we're not going to have crazy proofs, but these are little proofs based on the definition. So let's start off. Examples 12 and 13 are pretty solid in your book if you want to check those out. But let's start off with one that's not so bad. Let's take a look at a sub n is 1 over n squared. And let's prove a sub n is decreasing. Well, I'm already telling you it's decreasing. In just another moment or two, we'll do two problems. It'll be is the sequence increasing or decreasing? Prove your result. But here we're specifically saying decreasing, so we have to show this is true. Well, a sub n is already given. A sub n plus 1, again, it's notation, but we do this the same way we would use x notation. A sub n plus 1, replace the n with an n plus 1, preserve your relationships, and that is a sub n plus 1. So this is a sub n, this is a sub n plus 1. Is it true that this will always be bigger than this? That's our proof. We've got it set up. Now we have to show this inequality is true. And here's a couple of quick facts about inequalities. This one, we could literally just check off and be done. Now, I will show you. There's a lot of people like to cross multiply. Just make sure when you cross multiply, you always multiply this direction. To keep your inequality correct, you got to go this goes here and the answer stays here. This times this and the answer goes here. So by doing that, I still don't know it's true, but maybe I'm moving to a place where it's more obviously true. And this should be another spot that you could say, yeah, that's definitely true. Again, the nature of n always being a positive number, n plus 1 squared will be bigger than n squared. So either one of these are enough to say, yes, that is true, and a sub n is decreasing. But if you really want to take it further, maybe you're still not quite clear on that, FOIL this out. This will be n squared plus 2n plus 1. Now I could subtract an n squared from both sides and cancel. And now, nobody can argue this. You might have thought there might have been a little subjectivity here, and I'll come back and point out both of these in a moment, but there's no arguing this. Again, if n could be negative, like if n was -1, we would get -1 over here. But n cannot be -1. N starts with +1 and only gets bigger from there. So multiply that by 2 and add 1. Yep, if this is already positive, times 2 plus 1 is definitely positive, definitely bigger than 0. So for some people, that's their final line of proof to make this conclusion. But realize what we know about fractions. The reason you could make this conclusion right here is because you're lucky that you have the same numerator. So when you have the same numerator, we could just focus on the denominator. And bigger denominator goes with smaller fraction, right? Think about it with numbers. What's bigger, 1/2 or 1/10? If you eat half of a pizza or you eat 1/10 of a pizza, who ate more? The person who ate 1/2 of the pizza, right? Bigger denominator goes with smaller fraction. Now you can't do that if you have both changes in the top and the bottom. If I had 2 over 3 compared to 4 over 10, well, now I can't just compare this. You know, we really have to keep working in other ways. So that only works with the same numerator, bigger denominator goes with smaller fraction. Or in the second line, you could treat both of these like they're over 1. Now I've got the same denominator, bigger numerator goes with bigger fraction. Oops, should make that a 1. So here, we'd be in a bit of a pickle. This has the bigger numerator, so it feels like this is the bigger fraction, but this has the bigger denominator, so this feels like this should be the smaller fraction. Oh no, I had it right before. Sorry. That was the better way. So this feels like this should be the bigger fraction because of the bigger numerator, but this makes it feel like it should be the smaller fraction because of the bigger denominator, but we can't make that comparison. We can only make that comparison with the same numerator or with the same denominator. Bigger denominator, smaller fraction, bigger numerator, bigger fraction. So this first one wasn't bad, right? The biggest thing was just getting this set up, knowing the n+1 term, and then just seeing any one of these was really okay to say, yes, that is true, and make your conclusion. But now let's look at ones that are just a little bit harder. Let's take a look at n over n squared plus 2. So let's take a look at this sequence. And that previous one was a sub n, so I'll call this one b sub n. Slightly changing my directions. Is b sub n increasing, decreasing, or neither? Prove your result. Well, how are we going to make this decision? Well, let's look at a few terms, right? How do we know increasing or decreasing? The previous one I just told you was decreasing, but you know, let's take a look. Let's see what's happening inside of this problem. We'll also do this again with c sub n, and we'll do 2n plus 5 over n plus 1. And we'll ask, is c sub n increasing or decreasing? So let's plug in some values and let's see. So if I look at b sub 1, I get 1 over 1 squared plus 2, I get 1/3. b sub 2, I get 2 over 2 squared plus 2, 4 plus 2, which is 6. And I'll note that, hey, nothing even changed on that first line. But then b3, 3 over 9 plus 2 is 3 over 11. And maybe you're not even sure, but if you pull out a calculator, you'll see this is like 0.2727. So this is a smaller value than this one. Think we're decreasing, but let's do one more for good measure. 4 over 16 plus 2 is 18. If you want to reduce it again, some people, it's just calculators here, just so we can compare the decimals, that 0.333 forever. I get the same thing here, so no change, but then 3 over 11, the 0.2727, 0.222. So you could use your calculator to just get some decimal approximates to make it quick so you could see, okay, yes, this does look like it is decreasing, but now to go through and prove it to be decreasing, b sub n would have to be bigger than b sub n plus 1, b sub n, just as we saw, as given, b sub n plus 1. I don't know if this is true yet. I'm keeping my inequality. I should have just pointed this out at the end. This one I knew was true, so now by going backwards, all the previous inequalities must have also been true. Again, this idea of cross-multiplying, if you do it, there's no multiplying by a negative because all these are positive, so there's no flipping signs. Again, little advantages that we get from dealing with n and not x. But once we get to this line, now I know all the previous inequalities are true, and that's how I made this conclusion. So same thing here. I'm going to work on this inequality, hoping it's true, and then once I see it's true, I'll be able to come up and say, yes, this line was true. But what is b sub n plus 1? Replace all n's with n plus 1's and preserve the relationships. And this is exactly what we were pointing out on the previous page. Now, I don't know just by looking at this. I'm definitely going to have to manipulate in some way to see the result here. Because again, if I just look at the numerator, this is the smaller numerator, or this is the bigger one. So this feels like the smaller fraction. But then looking at the denominator, this is the bigger denominator. So this feels like the smaller fraction. So neither one of these are clicking together, so we're going to have to do more. And the easier way is to get rid of the denominator. So I'll get n times this whole thing, which let me just clean this up a little bit. This will be n squared plus 2n plus 1 plus that 2 will give me a plus 3. And this times this. Not obvious. I mean, maybe now people start plugging in values for n. That's not a proof, everybody. That's a demonstration. That's like people come right back up here and like, isn't this proof that you're decreasing? No, all that is proof that by the fourth term you're decreasing, but what about the fifth term? What about the sixth term? Doesn't matter how far you go, I could keep going. You take it out to B10, I say, what about the 11th term? What about the 12th term? This is the way to prove it generically. This gave us the idea was decreasing. Now we're trying to go through that proof. Not obvious here, still not obvious, but now let's start foiling and distributing a little bit. N cubed plus 2n squared plus 3n on this side. Over here, n cubed, I get plus n squared plus 2n plus 2. I'm trying to simplify. That's all I'm trying to do here. So what can happen? Well, again, some people might say, well, hey, these are the same, but this one is bigger here than this. But again, you're starting to argue a little bit, and you could do it algebraically. I could show these cancel, and that simplifies a lot. I could subtract this over. It doesn't cancel here, but I'm left with an n squared. Same here. I could subtract this over. It doesn't cancel. I'm left with an n. Is this always bigger than or equal to 2? Yes, it is. Once again, because n starts off with 1. And this is where I was saying earlier, if we had to do strictly decreasing, we'd have to make an extra note. This is actually equal when n equals 2. I'm sorry, when n equals 1. And then after, when n is greater than 2, then this would be true. But by including the equality, there's no extra note. You just realize maybe you're a little unsure, but once you see 1 works with this, then 2 and 3 and everything else works after, that's a good finishing proof. This now implies that this, all these question marks we had before are now confirmed to be the correct inequality because this is a correct inequality. And we get, again, that b sub n is decreasing. And one more, c sub n, same thing. We actually drew a graph of this, And we were kind of seeing that this was decreasing by just looking at the y's. But to do it again, C1, 2 plus 5 is 7 over 2. C2, 4 plus 5 is 9 over 3. I already went from 3.5 to 3. C3, 6 plus 5 is 11 over 4. That would be 2.75. Again, certainly looks like it's decreasing, but that's still not enough. And I only did 3 here, I did 4 here, because I wanted to see some confirmation. Here it was equal, so that didn't tell me anything. Now I saw this got smaller and then smaller still. So there's 2 cases at least of seeing the sequence decrease. Here, well, here to here was already 1 case, and here was even extra confirmation. So I feel good that C sub n is decreasing, but I've got to go through the proof, same that we did over here. So is C sub n greater than or equal to C sub n plus 1? Well, C sub n, as given, is that greater than or equal to n plus 1, preserve the relationships, 2 times n plus 1 plus 5, quantity n plus 1 plus 1. Same situation here that we had here. Which fraction is bigger, smaller? We can't tell. Here's bigger numerator, feels like bigger fraction, but this has the bigger denominator, so it feels like the smaller fraction. So like we saw over here, we're going to have to do more. So I'll clean up a little bit. This is 2n plus 2 plus 5, so that'll be 2n plus 7. N plus 1 is n plus 2. Cross multiply. Again, realize I can't just pick and choose. I got to do this times this and this times this, but I got to keep the sign in the same orientation. So it's got to be this times this over here. And similar, this times this over here. And just like we saw in this line, still not obvious. So I'll still leave my question mark. But just like we saw over here, if I clean it up now I don't have the fraction. Now if I FOIL things out, just so I don't run into this line, give myself a little more room, I would get 2n squared plus 5n plus 4n would give me a plus 9n plus 10. Over here, 2n squared. I get a 7n and a 2n is a 9n and a plus 7. What happens from here? I mean, right now, these are so close, you could say, yeah, now we could confirm this is bigger than this. You want to take it a little further. Unlike this one, where it's like, hey, we group some things together. These canceled, but this I just subtracted to combine. This I subtracted to combine. Once again, we're back in a good place where a lot of stuff cancels. And yes, you can conclude very safely, this doesn't even have n anymore. 10 is bigger than 7. I mean, take it a step further, subtract 7, and 3 is greater than 0. Either way, these are absolutely irrefutable statements. So all the inequalities were correct, and C sub n is, again, decreasing. Okay, the last little topic, the book does talk about being bounded, the sense that if you're thinking about the graphs, that there's kind of like this upper limit. This B sub n was bounded by 1. The points never went above 1. This C sub n was bounded by, I think, like 4 would be an upper bound. It's a nice term, but it's not something we're really going to need. So I'm going to try and get past that. And let's just get some more practice, and we'll finish section 11.1. You know, a lot of ideas, but now as we finish, we're just going to go back and we're going to answer a lot of those same questions that we were doing in the beginning. So, several problems. Let's start off. Give the first 4 terms for the sequence a sub n is negative n cubed over 2n minus 1. We're going to do a bunch of problems, so let's just start with that. There's number 1. Couldn't be easier. The first 4 terms, A1, A2, A3, A4. Honestly, some people could just start writing them and use the commas in between. That's fine. but others you want to be very clear as you plug in. Minus 1 cubed is minus 1. 2n, 2 times 1 minus 1 is 1. Minus 1. A sub 2, negative 2 cubed, negative 8. 2 times 2 minus 1, we get negative 8 thirds. A sub 3, negative 27 over 5. And one more, a sub 4, negative 64 over 7. And I'm showing you both because I don't mind how you give your answer here. You have a sub n, and he wrote out the first 4 terms after, but just again, be complete. This is not all of a sub n. It does continue forever, but you're clearly showing me the first 4 terms. That works. You do it this way, that works too. So that's all there is to it. Nothing to number 1 at all. Number 2. Let's find the general term, the general formula for b sub n. And let's take a look at, let's do 2 over 5, 5 over 7, 8 over 9, 1, 14 over 13, comma, dot, dot, dot. Again, just kind of the opposite. Here, you had the general term, asked you to find some terms. Here, you've got the terms trying to get you to get the general formula. Little things, just going back to number 1 very quickly. Numerator, denominator. Well, everything's negative. There's a negative sign. 1, 8, 27, 64 should stand out as perfect cubes. And they perfectly match. When n was 1, we had 1 cubed. When n was 2, we had 2 cubed. It was an absolute perfect match. Well, what about the denominator? 1, 3, 5, 7. I see a pattern. I see every time the denominator is increasing by 2. So I start off with a 2n in the denominator. But it's not perfect. If it's just 2n, this would be a 2. This would be a 4. This would be a 6. But every time I'm 1 less than what I just said, the minus 1 keeps it balanced. So I did that quickly because that wasn't what we were asking here, but just trying to point out how you can go back and forth. Some are easier to see than others. This one wasn't terrible. This one's not bad either. Once again, thinking of numerator and denominator separately. This seems weird, but we'll see why that is in just a moment. But as I start going through, looking at the top, 2, 5, 8, weird, 14. So let's leave this out for a moment. Thinking about this, it looks like I'm getting, I need a 3n. I keep adding 3. If I was multiplying by 3, I'd have a 3 to the n power, but I just keep adding 3, so I get a 3 times n. But when n equals 1, 2, 3, 4, 5, when n is 1, this would give me 3, but I'm getting 2. When n is 2, this would give me 6. I'm supposed to get 5. This would give me 9. I'm supposed to get 8. I'm 1 bigger than I should be, so I'll subtract 1 to keep everything balanced. I'm ignoring 4 for the moment, and I realize that still works for 5. When n is 5, 15 minus 1 does give me the 14. Well, what about the denominator? Now I'm consistently adding 2, 5, 7, 9, not sure. Again, that's still a weird one. So use these, 5, 7, 9. And here we would get that consistent adding 2 would give me a 2n, but this would only give me a 2. It needs to be a 5. This would only give me a 4. It needs to be a 7. Would give me a 6. Needs to be a 9. This time, I'm 3 short every time, so I would just add 3. Okay? And now I see it matches. Again, test n equals 5. 10 plus 3 gives me the 13. It works here. Well, now we kept saying this was weird. Well, if I use n equals 4, this was good confirmation, but why the heck does this seem so strange? If you plug in 4 here, 12 minus 1 is 11. 8 plus 3 is 11. Ah, they reduced it. This is how you should see it, and now the pattern is perfect. Plus 3, plus 3, plus 3, plus 3, plus 2, plus 2, plus 2, plus 2. But they already reduced it. That's why we were missing the pattern. Okay, we're going to get a tiny more with that, but I want to show you just one other quick thing. Similar, find the general term, but let's just take a look at this really quickly. Let's look at 1/2, 1, 2, 4, 8, ... What I want to show you, just coming up here, what we've kind of seen through a few examples is like weird stuff sometimes happens later on. So use the earlier terms to find your pattern and use your later terms for confirmation. That's not always the easy way to do things, everybody. It's all about finding the pattern. So if this one, let's call this one C sub n. So when n is 1, 2, 3, 4, and 5, these are what we're getting. But what's the pattern? Maybe you see there's a times 2 in here. How do you go from 1 to 2? Well, you add 1, but then if you add 1, this would only give you a 3. That pattern doesn't work. A pattern only works if it works all the time, not just here or there. But 1 times 2 gives me 2. 2 times 2 gives me 4. 4 times 2 gives me 8. Even going back to the beginning, 1/2 times 2 gives me 1. So that pattern does work. So that should make us feel that we need a 2 to the n. But just like we were seeing here, these fit that pattern of consistently adding 3, consistently adding 2. This fits the consistently multiplying by 2, but these are the adjustments to make everything perfect. Because if we go backwards for a moment, notice these are powers of 2. This is 2 cubed, 2 squared, 2 to the first power. Well, how does this fit that pattern? Well, maybe you don't see it right now, but these later terms, how can I make this match? When n equals 3, I need 2 to the first power. When n equals 4, I need 2 squared. When n equals 5, I need 2 cubed. Every time, my exponent is 2 less than what the n value was, 2 to the n minus 2 power. And now, well, what happens if you go to the earlier ones? If you didn't already see how this pattern was working, well, when you plug 1 in here, you get 2 to the minus 1. That is 1/2. You plug in 2 here, you get 2 to the 0 power. That fits, that is 1. So this would be your general formula for C. Okay, so a little bit of general formula, but now let's finish this whole unit. Been a lot here. Let's go back to the whole do the following, converge or diverge. If they converge to what? Number 1, let's look at a sub n that we had up here. Taking the limit as n goes to infinity. Now, I know some of you could do a lot of this work in your head. I don't want you to do too much, by the way, but you know, some of these limits you've seen, I'm doing things fairly quickly. Some people are very comfortable with some of these limits, like this one is not that bad, but you need to show me something. So even if you just write this, a sub n, and then get your conclusion, that's enough. That's what I was doing on the previous pages. That shows me you know what you're doing, and then I understand you're just doing that limit work kind of in your head. You could certainly show me negative n cubed over 2n minus 1. I'm going to use the dominant terms. So negative n cubed over 2n. 1n would cancel, so I get negative n squared over 2. That goes to negative infinity. So a sub n diverges. I mean, that's every step of the way. You could do it like I keep saying. You know, you just want to write a sub n. Maybe you want to just jump to the dominant terms. There's little things you could do, but you have to show me work. If you just write diverge, maybe you knew that this went to negative infinity, but without showing me that, that looks like a guess, and a guess gets no credit by itself. So again, it's not just the right answer. You have to have the work to go with it. So number 2, we're still converging, diverging. And now let's do it for B sub n. Remember, B sub n was not given by the general formula. B sub n was given by these terms. So if you want to figure out, does this converge or diverge, you'd have to do the general formula first. So I'm going to take advantage, we already did that. But again, if I just gave you the problem like this, does this sequence converge or diverge? That would be step 1. That's why we'll continue to get more practice finding the general term. That is, you know, it's more common to be given the general term, but there's enough problems where we're just given a bunch of the terms. So we do our work. To get this general formula, and this is what I was saying. I think this limit is actually a little easier than this limit. So I give you permission, but you got to show me something. You set this up. You don't even write the general formula. You already have it here. The limit of B sub n. You focus on the dominant terms. You'll get 3/2 or 1.5. So B sub n converges. Again, fraction, decimal, that doesn't matter. 3/2, 1.5. And I don't want to just highlight that. The whole answer is that it converges and what it converges to. All right. Still want to do a couple more. So now, still converge, diverge. Number 3. Let's look at the sequence. What are we up to? I guess that would be D sub n. I use C sub n already. D sub n is 0, 1, 4, 9, 16, comma, dot, dot, dot. Exact same thing we just saw a moment ago. Converge, diverge. Well, I mean, maybe you can kind of see, drawing the graph, you might get a little bit of a good sense. But the best way, get the general formula. N is 1, 2, 3, 4, 5. These are perfect squares. But when we have 1, we're getting 0 squared. When we have 2, we're getting 1 squared. When we have 3, we're getting 2 squared. 3 squared, 4 squared. The general formula for D sub n, I'm not just getting the n squared, it's always n minus 1 that is being squared. And that's fine if you want to FOIL this out, that's an alternative. So once again, the hard part here was really just getting the general formula. This limit goes to infinity. So D sub n is a divergent sequence. Last 2. Number 4, we'll do E sub n is 4n plus 3 over 6n minus 1. Limit of E sub n is 2/3. I went a little faster there, just trying to point out. Some of you can do that, and that's perfectly fine. I need something, okay? Just giving the answer without any work feels weird. At least convergent, you're also pointing out what it converges to. So that gives a little bit of a better reinforcement that you really know what you're doing. But just that little bit of notation makes everything clear. You want to do some more, the limit of all of this. You get to break it down just to the 4n over 6n. Again, L'Hopital's rule, make sure you convert to x's. And the same thing for number 5. And this is our last one, everybody. F sub n, let's look at 2n cubed minus n plus 4 all over the square root of n to the 6th plus n to the 4th plus 1. Quite a big mess, but still taking the limit. Even with the square root here, this still works with the idea of dominant terms. Biggest term from the top, biggest term from the bottom. But just notice the biggest term from the bottom includes that square root. So now Dominant term allows me to get rid of all these other terms, and that still allows me to simplify. Just realize right here, we start by simplifying that as n cubed. Now the n cubes cancel. The limit equals 2. So f, the sequence f, converges to 2.